This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
Hello, this is Simon Crossley for Software Engineering Radio. Today I'm speaking with Simon Riggs about advanced features of the Postgres database. Simon is a professional developer and consultant with lots of experience with a variety of database technologies. He's a regular conference speaker on database technologies, and I first met him several years ago at a Postgres user group meeting where he's presenting some of the clustering and replication features that he's committed to the Postgres database. Simon's continued to contribute major features to Postgres, and as CTO of Second Quadrant Consultancy has built a team of developers and consultants delivering advanced Postgres implementations to enterprise clients. I hope that introduction does you justice. Simon, and welcome to Software Engineering Radio.
Thank you very much.
Postgres is widely promoted as the world's most advanced open source database, and today I'd like to talk in detail about some of those advanced features. But first, could you please summarize the ways in which you think Postgres is more advanced than other databases?
Sure. Well, I think the first and foremost feature is that it follows the SQL standard extremely closely. Now, that may not seem like the most advanced thing, but the standard is long and complex, and it takes a lot of work to get us to match that closely. But in general, Postgres has got broad and very deep feature support across a whole range of different use cases. And it's my view that Postgres is more than just a relational database, and I'd like to explain that to you if we go in that direction. A couple of other things I'd like to mention as to why we're the most advanced. The query planner and in general performance is very advanced in Postgres. For example, there are 6 different types of index available with Postgres, many more than most other databases. And Postgres also invented the partial index and expression indexes, both of which are very useful for performance. Postgres is also very extensible. We pretty much invented that thought, and that brings in a whole sort of vast array of add-ons that you can get with Postgres that other people need to add themselves to the core engine, whereas Postgres can just expose an interface to allow people to add their own things.
Okay.
But the last one is actually ease of use, which is a strange one because, some people would say in the past it was hard to install and that kind of thing. But the main thing with Postgres really is it just works. And we design things in a way that causes the least surprise for developers. And we also go to a lot of trouble to ensure it's robust and accurate. For example, a couple of years ago, we discovered that there'd been some minor error in the accuracy of one of the functions, and I think there was sort of 10 decimal places into the results. There was some weird error, and we spent a lot of time fixing that. Now, that kind of attention to detail is what makes Postgres the most advanced, because it takes time and it takes love and care really to make the feature set full and complete.
Yeah, that's definitely something we can appreciate, and I know that you've personally spent a lot of time doing that and the team of people. And thanks for that excellent list. I think that'll give us a good structure for our conversation. So let's start at the top and let's return to some of the features of the SQL standard, which you said Postgres has good support for. I think most of our listeners will be familiar with the select statement, but there are lots of more advanced features SQL that maybe they're not that familiar with. What are the things that Postgres supports that developers might be unfamiliar with but could be useful for them in their work?
Yeah, so there's some interesting additions to the SQL language that people are just simply not familiar with. Obviously, people have heard of things like joins and subselects between tables.
Yeah.
But we've extended the insert command, which allows you to implement something that does what's known as an upsert, in that it will attempt to do an insert, but if the row's already there, it will turn it into an update. So that's one of the first things.
So instead of getting an unhelpful conflict error, your statement will just work.
It will just work. And what's more important there is that we spent quite a lot of time designing it in a way that means that it is guaranteed to give you an answer. It doesn't just sort of whirl around forever without deciding what to do. So it's quite a subtle implementation, and it took actually multiple years to get that to work. So that was time well spent, because it saves time for the user.
Okay, excellent.
So moving on from there, my next point of call, I think, would be window functions, which is something that, frankly, many people have never even heard of.
Yeah.
But a window function is something that allows you to look at the results of a query in an ordered way. For example, if you're looking at a time series and you want to look at the last 3 points on the time series, then you need a window function. Now, a lot of people think that that's not possible in SQL, and it wasn't. In the early versions of SQL, it was quite a simple language, and SQL did, more than 20 years ago, receive criticism for some of the things it lacked. What people don't realise is that those things were added to the SQL standard, and Postgres has supported them for many years. So, for example, if you want to look at a time series, you want to calculate a moving average over data, if you want to look at a lag, these are all things that can be done in the SQL language, and done not just, we can barely touch them. I'm talking about implementing fully with decent optimization. So it's been implemented for more than 10 years, and it's been highly optimized. So that's the first thing.
What are the keywords that you would use to structure a window function in your SQL statement?
So there's an over clause which allows you to calculate aggregates across a window clause, and then you can structure things so that you can say what type of window it's going to be, whether it's a moving window or whether it's a window that goes back to the beginning of the series. So you might have a cumulative total alongside the total, for example. So you can list out a range of numbers with a cumulative total alongside them, or you could smooth out your data across a number of different points, as I said, to calculate moving averages and that kind of thing. So there's a lot of complex statistical functions built into Postgres, and that is one of the ways that we support them.
And so, in your example of a time series and choosing the last 3 points,
yes.
If my timestamp column is the series that I'm interested in, then I would run my window over the timestamp column and then perform some statistics or other calculations on the resulting sets.
Yes, so the results there are actually called window aggregate functions, and so you would, for each row in the table, you would access the sliding window, and then you'd calculate the result of the aggregate across the sliding window.
Okay.
So, yeah, and please don't ask me what the syntax is, because I have to look in the manual as well, right? But that's not the point, is it? It's whether it fully supports the standard and does so in a useful and performant way.
And I think that importantly as well, it's the code that a developer would have to write client side in order to do that work. and to do that work in a way that's performant and works over large data sets, it's that Postgres has that power, right?
Yeah, very much so. Yeah.
Yeah.
Another example of how we handle that is there's a thing called a with clause that allows you to define what's called a common table expression. So that allows you to define a fragment of code that could be reused many times within your SQL. Obviously, that kind of thing makes it much more sensible to write correct code, because if you have to have sections of code that are similar, then that avoids mistakes. But the interesting thing about the with subcommand is that we support the with recursive form, which is actually in the SQL standard. And what that allows you to do is to search a network or a hierarchy. And quite surprising to many people is the fact that that allows you to write graph queries inside Postgres. And most people believe that's not possible, and yet it is actually completely possible, and not just possible, very well performant, in that it's been fully optimized as well. So there's some really impressive features in there that I used in production in many parts of the world.
So how would I need to structure my data in order to be able to run a graph query recursively over that?
Well, the main thing that's needed is connections between the data elements. We don't impose a fixed structure on your data before you can use a graph query, which some other approaches do require you to have a sort of strict structuring. So if you have the old example from years ago was the employee table, where employees have managers and their managers can have managers, and you can write a recursive query that sort of says, what's the total salary of all the people in my department, for example, and you would start with you, go out from there in a graph, moving from employee to employee. And it isn't something where for each link you need to write an extra join. You can actually do that recursively. So it doesn't matter how deep the hierarchy or the network is, you can still search it. So we're not limiting you to a particular sort of property graph model or something like that. You can use any sort of data. So it could be XML data or JSON data that's there, and you're following links between data items. So all of that would be fully supported.
Oh, okay. And the common table expression is when you say it's a with clause.
Yes.
I'm thinking that it's a definition of a view within your statement. Is that the right way of thinking about those?
Especially when you're doing so the with clause is just a sort of a fragment of code that would be reused. But the with recursive, you have a starting point for the query and then an iterator that moves you to the next data item. Again, these are very advanced features of SQL that most people don't know about, and Postgres fully supports. So
yeah. Excellent. Maybe now's a good time to move on to the broad and deep feature support, because you specifically mentioned there that it's not just SQL.
Yes.
In the database, and that sounds something interesting that we should explore.
So what's happened over the years is that Postgres, because it's extensible, it's actually been used as a platform for development of wider features. For example, GIS features were added by the PostGIS project, and that's all been done by using the extensibility features, user-defined functions, user-defined data types, various types of indexing that have been added. And as a result, the PostGIS package implements the full GIS standard for use within Postgres. So Postgres, when you plug that in, becomes a GIS database as well. But there are similar sort of use case packages in full text support, other document support, And we're also now realizing that Postgres actually already has graph support, and we're adding time series capabilities as well by the fairly recent partitioning support that's been added. So the functionality really doesn't just go in one particular direction. It covers a whole range of use cases, and that's what makes it a very useful general purpose database, because if you've got a database and it has a little bit of graph, a little bit of GIS, some text, some normal relational features, it can accommodate all of that all at once in the one application without you needing to resort to sort of microservice architectures.
So what kind of features, what kind of functions could I perform with a GIS database?
I mean, it's really to do with viewing maps and map data. So the PostGIS package maps the world as if it was coded onto just a flat surface, and then you can look at things in terms of sort of bounding boxes and lines between nodes and things like that. So it's actually extremely complex, the support. It goes well beyond what your average database person would imagine. And it's actually a real sort of world contender now. It's used for extremely complex GIS applications. Basically, there's a whole industry out there of people looking at geographic factors, and they store everything in PostGIS. So it's quite a wide domain, and very often there's not much crossover.
And can I build indexes using geometric features and make that performant?
Yeah, that's one of the great things here. Actually, there's multiple types of index that you can build for that. So there's the equivalent of R-tree support, which is pretty useful, and then there's a KD tree that we can use. So there's actually multiple styles of index which have different properties depending on what types of things that you're looking to optimize, whether you're trying to optimize search time, or whether you're trying to minimize the size of the index, or optimize for maintenance of the index, for example. These are all things that you can sort of select your choice of index type depending on your use case. Sorry, it's so complex, right?
Yes,
that's the thing I'm trying to get across, really. So,
and that's all kind of through the PostGIS extension. That's how those features are added into the database, and a similar set of features for temporal data and for the other additional types.
Yeah, so we did actually have the text, full text stuff as an external package, but some years ago that was brought directly inside the server core. So we've got full text support actually in the server core. But the indexing that I was describing there, the index types are part of the core server, but some of the implementation exists in the external packages. So, for example, there'll be an external package that implements a particular data type, and then searches on that data type would use the internal index mechanisms. But yeah, I mean, basically it's not just one database, it's many databases, because you can build the types of support you need in to give yourself a kind of integrated platform. So I really think of it more as less of a database and more of a data platform.
Okay, and the full text support, will that cope with free text and structured text, or?
Yes, very much. So we've got a stemmer package built into the core. There's quite advanced full text support. You can set up dictionaries and stop word lists, and there's quite an extensive range of features there. It's by no means a trivial sort of box tick feature. It's it's the full deal, really.
And does that have a query interface that just slots into SQL? Is there any special keywords that I need or to have access to?
Well, a lot of it is done via functions. The actual configuration of it allows you to set up parsers and dictionaries, and you can have dictionaries in different languages and that kind of thing. So it's actually a full and complex support, which also supports collations and that kind of thing. So it's not something that I want to delve into in massive detail on a call. I mean, I could spend a whole call just on that topic, but
yeah. And are these extensions that you're talking about? Are these are different from the foreign data wrappers?
Yes. So the foreign data wrapper is an API that allows us to write access packages to other databases. So, for example, there's packages written that will allow you to access MySQL or Oracle or very sort of generic JDBC data sources, and that will if what you do there is you set up a thing called a foreign table, which is essentially a stub. We access the stub. The SQL then gets passed through to the remote server. It will execute a query and then bring data back to us. So that really allows Postgres then to become a kind of data hub across all the different database types. And I know that that's quite popular with MongoDB, who use the Postgres technology to give you access to their own data store. So.
That's really interesting. You used the words data platform and data hub. It's really extending the concept of a database.
Well, I think that's really the where we're going, because time was when you put stuff in a database, it just kind of sat there until you got it back out again. Now there's much greater requirement for it to do something useful. In the age of business intelligence, we need more from our data than just simply a storage mechanism. Obviously, you need to depend upon those basics of storage and high availability and backup and that kind of thing, but working beyond that, it has to provide a wider range of functionality to fit in the modern enterprise. There's too much going on to just store it and then bring it back again. It's not enough just to do that anymore.
Okay, so you have features that you can help process the data as well. You mentioned the query planner.
Yes.
As being advanced. If you're handling all of these different types of data, I can imagine you're putting some real heavy loads on the query planner, being able to optimize queries in all these different scenarios.
Yeah, I mean that's interesting point. You might imagine that some of these things aren't fully or properly optimized. Well, what we've also done, as well as extend the database, so you can add user-defined data types. But with those user-defined data types, you can also add into the database statistics collection routines that are appropriate to those data types. And so as a result, you can write a query that says, give me all the data in that bounding box, and it's all fully optimized. And what we've done is just sort of extend the statistics system and the optimizer to cope with it.
Okay, so as well as extending the types of data, you extend the query planner and the optimizer to be able to handle them as well.
Yes. By extending the support for new types of statistical data about those data types.
That's really interesting. And you've also talked about the different indexes in here. So you mentioned a couple of indexes for the GIS data types. Are there particular types of indexes that developers might not be aware of to use in Postgres?
Definitely. So the basic index type that everybody will be familiar with is the tree or B tree index type. Then people might also have heard of a hash index, which allows you to go straight to the data without sort of navigating the full tree. We've also extended that, so if you've got data that is located by date or by number, you can use something called a block range index, which is a very small index type, so it's designed for very large data. We also support an inverted index called a GIN index, and there's another two index types called a GIST and an SP GIST. And these, the G in all three of those last index types mentioned stands for generalized, and there's been a lot of research in the last 10 or 20 years about generalized search trees or generalized indexing mechanisms. And some of this research to create these concepts was actually sponsored by the US government. And that work has been taken and put into Postgres. So as a result of that, we now support not just different types of index, but index mechanisms that can be further extended themselves. And that allows you to support multiple different kinds of structuring within an index that allows it to work efficiently in different ways. Gosh, I'm not even going to try to explain some of those things on a call, but the main thing is it gives you options, and you can use those options to make some good decisions about how to index different types of data.
What would be a good use case then for one of these generalized index types?
Okay, so Postgres was actually the first database to implement something called nearest neighbor indexing. So if you, for example, were holding your mobile phone and you want to press it and say, "Show me the nearest coffee shop," you might think that is kind of an easy type of query, but it turns out it's not. Because you need a specialized index type that will cope with the fact that you're actually looking at things near you, not rather than in a specific place. And Postgres was the first database to implement that type of query via an index. Previous to that, people used what was called bounding box techniques, and they were at least 10 times slower. So Postgres implemented that using an index. It's called nearest neighbor indexing.
Okay, and is that a calculation between 2 points?
Exactly, yeah. So it sounds quite complex, but if I showed you the query of it, you'd go, okay, yeah, that's pretty easy to write. So basically, we just have a column that says location. We put the specialized kind of index on it, and then we just use a particular form of where clause to retrieve the rows from it. And it works using an index rather than doing some kind of full data scan.
Okay, that's interesting. So is that you're indexing with an expression?
Yes, that's correct. So you can look it up. Basically, it's K nearest neighbor, or KNN indexing, allows you to look at the data points that are nearest to you, and then obviously you would put an extra filter of coffee shop on that in order to spread things out and make that into the search that I described.
Oh, that's good. Are there other uses of expressions within indexes?
Yeah, I mean, we support expression indexes as well, so you can build an index on, the first 10 characters of a field, say, or you can, index, any expression that you can execute. So any function that would retrieve a result from a column can be indexed. So it's quite advanced functionality. We also support partial indexing, which means you can index all of the rows that aren't null, for example, rather than having to index all of the rows in the table.
So that can save space and improve search performance?
Absolutely, yeah, exactly those two things, yeah.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. DigitalOcean stands out from the crowd due to its simplicity, high performance, and no billing surprises. Join a community of over 3.5 million developers on DigitalOcean. Sign up with a free $100 infrastructure credit at do.co/SERadio.
Obviously, indexes are core to making a database performant. Is there anything else that we should cover with indexes, do you think?
Well, I mean, there's many other good features, but I think one long-term guy at one of the other vendors was asked a question on his retirement: if he could go back and spend more time on, what would he spend time on? And he just replied, indexes.
Right.
And as a result, that makes me think we've done the right thing by having the easily the widest and most complex set of index types of any database, even beating commercial.
And that's referring back to this concept of these generalized indexes and their extensibility.
Exactly. Yes.
We keep coming back to extensibility, and it sort of really does seem that Postgres core functions have been built from extensions over the years and pulling functionality in. Are there other particular extensions that are interesting and relevant at the moment?
Well, I mean, there's actually what this creates is actually an ecosystem of tools for people that want to build additional functionality in the system, but they don't want to spend the time to bring it into the core server. I mean, we release on what was once regarded as quite an aggressive timescale of annual releases. But in terms of, if you're trying to build an application, you can't submit something to Postgres, then just wait for the next release, because that's basically 12 to 18 months. So if you want new functionality now in your system, you can build an extension and you can get it within 1 to 3 months. You can have that functionality built into your database. So it's a way of expanding the functionality of the data platform, but it's also a way of delivering that functionality in usable form for applications, so delivering it quickly as well. But as I said, what that's done is it's created a whole ecosystem of hundreds of small tools and utilities and plugins, all of which together make Postgres into a whole range of powerful different things. So it's not one thing; it's anything you want it to be.
Okay. If are these extensions difficult to write? Are they complicated interfaces that I need to understand to write one? Well,
Postgres supports quite a range of internal APIs that you can have access to. A lot of the extensions out there are open source, and so you can copy an existing one. So really what you need to work out is which APIs should you be using to provide this additional functionality, and how am I going to go about using that? Obviously, if you're building an extension that you expect thousands or millions of people to use, then you need to go to a lot more care in the development of it than you would do on a sort of single function just for your usage. But so there's a whole range of sort of emulation functions and monitoring facilities. For example, Second Quadrant publishes the multi-master extension, BDR, for bidirectional replication. And that is available now as just an extension to the database. So it just plugs straight in and away you go.
Okay, so that's that's obviously an advanced feature, data replication, going beyond just handling different types. Postgres performs that job very well. Maybe to just describe the concepts behind the replication.
Yeah, sure. So we support a couple of different kinds of replication. The first kind is physical replication, where we actually take a copy of the transaction log and we send that to another location. And by doing so, we're able to offer high availability. So if you stream that in real time to another server, then you can have the choice of sending that asynchronously, meaning you commit your transaction and then you send the data somewhere else, or you can do it synchronously, where the commit waits in a queue until your data has been sent to a secondary server, and then it returns. So you get your choice of whether you want to add latency to give you protection guarantees, or whether you want speed in that the commit will come back to you quickly, but you don't yet know whether your data is safe. And Postgres actually does that in quite a clever way, in that we allow you to make that choice at the individual transaction level. So you can have some transactions that you consider important ones being committed synchronously, and slightly less important ones you can have executing much faster asynchronously. So that's the physical replication. What we then do is, when we ship the data to a secondary server, we run that server as what's called a hot standby server, and you can actually execute queries on the standby nodes. And what you can do there is you can add as many standby nodes as you want to give you a full server farm where you're able to execute thousands and thousands of queries across the many different servers. So that allows you to effectively have an extensible cache built of additional servers. We also support cascading replication, which allows you to have those servers connect together, so you can actually have a hierarchy of standby servers, so to give you a full server farm. What we also have is something that we've introduced in the last couple of years, is called logical replication. And this is where we only send the data changes, not the whole transaction log. So the first reason is that saves bandwidth when you're sending it across region. But the other thing is that the logical replication is much more flexible, and we can actually use it as some kind of real-time data pump to other applications in the enterprise. And most importantly, we can send it to other versions of Postgres. So as a result of this functionality, we're able to do a full online upgrade. So a near zero-time upgrade, zero downtime upgrade of your servers. And obviously that's what people are looking for now, is to never take their systems down.
Okay, so you can maintain availability because it's a logical replication.
Yes.
You can only physically replicate the transaction log between identical versions of Postgres.
That's correct, yeah. So even though it's quite an efficient replication mechanism, it's not one that works cross-version. And so if you want to publish data across to a remote site, you really would prefer the logical replication mechanism, but it's because of its ability to go cross-version, it allows you to continuously upgrade. Every time there's a new major version comes out, you can upgrade fairly soon to that. You don't have to wait 3 years for the next sort of window of opportunity, which is what used to happen in the old days.
If I want to build a high availability system with a large amount of data in it, what kind of orders of magnitude of numbers in terms of database size and bandwidth, what am I kind of looking at for the capabilities I need from my hardware?
Well, I mean, things are very efficient now, so I would not like to sort of throw too many numbers at you. I can tell you some sizes of things, but it really does depend upon the hardware that you spend your money on as to to what kind of performance you're getting out of this. But there are Postgres databases out there that are above 50 terabytes on a single node, and it's very frequent to see databases above 10 terabytes or above a terabyte. So I would have said that most of the customers that I deal with personally are systems above a terabyte in size. And they have extremely high transaction rates. I think that's the other thing that's changed in recent years. It isn't uncommon to see transaction rates of more than 1,000 transactions a second, and in some cases you'll see above 10,000 or more. In many cases, So it's, the amount of data flying around now is really quite extreme, and it's difficult to get your head around the differences between sort of low end transaction rate systems and the very highest transaction rate systems. There are people out there that are really pushing the barriers back of what's possible.
Is that where you would need the farm of services in order to really get the optimum use from Postgres in those scenarios? Do we look at parallelizing queries and things like that to get those to run?
Yeah, so parallel query currently with core Postgres operates only on a single node. So if you've got sort of 4 or 8 CPU systems, then you can get some decent parallelism going on those single nodes. In terms of Postgres operating across multiple servers, you'd need to be looking at something like PostgreSQL before you could operate across multiple nodes. So it's a few years yet before core Postgres itself will provide that functionality. But again, there's different versions of Postgres and different packages that you can get that enable that type of functionality.
Okay, interesting. And is that replication something that is being actively developed at the moment? Are there changes in future releases?
Yeah, I mean we've just made a load of changes in Postgres 12 that relate to how the configuration works, and there's been pretty continuous change in the replication functionality over the years. I mean, the streaming replication feature went in 2010, and then there was a sort of big surge of work after that. But actually, the amount of change has stayed fairly constant. It's what I think is surprising is that, or maybe it's not surprising, but because people are using it heavily in production, they've got lots of small requirements for performance changes and things like that. So, for example, about 18 months ago, I spent a lot of time myself working on replication latency, and we removed sort of various bottlenecks that were occurring there. Each of those things takes quite a lot of work, but obviously it's what you might call polishing work rather than initial feature development, but it can still be very complex. So there's lots of things still going into Postgres. It really, I think that's the surprising thing when you call it the most advanced relational, most advanced database. You would think that we would be feature complete, but it's actually the opposite way around. The more users we have, the more demand there is for new features.
Right. Your work will never finish.
Yeah, it looks that way, yeah. Yeah, thankfully.
And we talked about some very advanced use cases there, some very high volumes, high transaction rates. But back at the beginning, you mentioned that Postgres is easy to use.
Yes.
In install and use. So is that a journey from your first install to the multi-node server farm? Can you talk us through what that journey might look like and steps on the way?
Well, I think, especially with the replication stuff, I know that people will say, oh, replication is really complex, but believe me, we've simplified it a lot from the way other vendors have implemented it. So, for example, in order to make your application synchronous, you only have to touch one parameter to change that. And the number of application parameters overall is relatively small. So, what you need to do to get the servers to work together is you just set up a node with the software on it, and then you can launch what's called a base backup to copy the initial server.
Yeah.
And then you start it up, and it will begin talking to the master node, and it will bring across all of the changes, and it will just continue to work. So these things, obviously we have made it even simpler over the years, but in essence we designed it from the very first go that it was going to be as simple to use as possible, and with very few parameters and commands. And I think we have achieved that. Obviously, as more people add complexity, the parameters emerge. But in order to build up a whole server farm, you basically just point the standby nodes at the master and then begin flowing the data across. And these days, that is just a single command in order to get it to begin the backup and begin the sending of the transaction log.
Okay, and if I had, a 10 terabyte database or something, and I wanted to replicate that, that's obviously going to take some time, even with a very high bandwidth connection. What sort of monitoring would I need to have in place? How would I know that I was caught up and in sync, or if I was ever falling behind?
Yeah, so I think that's one of the things that's taken longest to build in is actually the decent monitoring facilities. But we do have the capability now to manage and monitor the replication lag. We can measure that as an amount of time or as an amount of bytes. We don't actually yet have something that predicts how long it will take to do the full backup and start, but that is something that I actually wrote the spec for just today, in fact. So that's.
I'd never believe a progress bar, anyway.
Well, yes. I mean, that's the funny thing. I mean, obviously, as we're sitting here discussing it, everybody's got the same feeling about progress bars and not trusting them, and that's why we wanted to if we do this, we have to do it properly. We can't just have something that kind of sort of works when you squint. So.
Yeah. Okay. And is there anything else that you wanted to include in sort of ease of use?
Well, I think robustness is ease of use. If something breaks all the time or just gives you strange messages, then that's very frustrating. So robustness is and dependability means that you can hit your deadlines, you can trust the software. Accuracy means that you can always trust that we've done the right thing. We haven't truncated your data or sort of set it to null in weird circumstances or something like that. And when you go to use a feature, you can also trust that it's been implemented in complete form, and as a result of that, you can actually use it, with a good level of trust. Security these days is also a big feature, but I'd really call that an ease of use feature, because if something doesn't have security, then that then you have to go to some level of difficulty to isolate it so that it can stop it from being attacked. Whereas with Postgres, you've got that level of trust there that we've done a lot for you in terms of security. So.
And what kind of features would you include in security? Yeah,
so I mean we've recently updated the authentication technology to 256-bit encryption. That's pretty advanced. That's called Scram, and it uses an underlying API called Sazzle. So what we've done there is we've implemented the very latest technology, but also implemented it using the API that will allow us to keep up to date as much as possible with that technology as it evolves.
Okay, and so that's authenticated access to the database. Is that right?
Yeah, that's right. We also implement something called host-based authentication, which is basically allows you to whitelist or blacklist different addresses or IP ranges and that kind of thing. So it really allows you to control the level of security that you've got in the system. And if somebody, for example, tries to access the system with a user ID that doesn't exist, we don't reply with things like user ID does not exist, because obviously that's information to the person trying to hack the system. So we go to a lot of trouble to make that look like it's a valid user, but you just didn't know the password, for example. So
okay, yeah, that makes complete sense. Good. Is there anything else that you would particularly like to mention? We've covered a lot in this conversation, but I'm sure there's a lot more.
Yeah, well, I think the there's a couple of things out there. We've got very well thought out support for time zones, good internationalization support, and we also support something called serialization, which is a mode that allows you to trust that the data in the database makes a lot of sense, what's called transaction isolation. There are various access problems that people are simply unaware of, that databases go to a lot of trouble to get right. And if you just access a data store that's got no thought given to the transaction isolation modes, then it does make it harder to use, because you get strange problems with numbers that don't add up, and data that appears to have disappeared, and phantom reads and that kind of thing. There's some strange anomalies.
So these would be when there are concurrent modifications being made to the database.
Exactly so, yeah. The basic physics of it, because if you've got data's in two places, if you look at the first data location and read what it says, and then you come back and then you go to the second data location, well, obviously during that pause the first data location can have changed, and you can get into a sort of strange situation where if you try and add up the values in two separate locations, you can end up with a value that never existed in the database at the same time, for example, because you're looking at one and then you're looking at another.
Yeah.
And so there's quite a lot of support in the database for levels of care with that. So obviously if we're handling money, for example, you don't really want to be looking at your bank accounts and have them not add up, for example, right? So that's a pretty serious situation. And that's if you access data in a pretty simple data store, then you don't get that level of coverage. You don't get that level of protection. So we go to a lot of trouble to explain the types of sort of physics data anomaly that can exist and what you should do about it.
And when we were talking about replication, you could control how the data was replicated at the transaction level. Are there controls in place for different transaction isolation levels?
Yeah, I mean, so within the database you can specify the type of transactional isolation level you wanted at the transaction level. So you can specify it for the whole database if you want, but you can actually request different levels depending on the type of data manipulation that you're planning. Obviously, making that work across nodes is significantly harder, and that is something that we're working on right now. But it's obviously an important thing for the future. The only problem is that physics is against us there, because there's various theorems that say that you can't have it both consistently and quickly.
Yes.
And yeah.
I've always thought of Postgres as being the database that would provide you with the consistent answer and the accurate answer.
Yeah.
And is that right, or is that again something that's tunable?
Well, it's that is our hope by default. That was always the default we would pick, but we recognise there are times when you really do need it to go faster, and you might be able to prove that your transactions are in fact correct for some reason, and so you're happy to turn things to a sort of potentially less safe option. For me, I think it's important to have that user control over performance v robustness and consistency. I think that's quite an important lever to say, look, I need it quick, damn it, as against, look, I need it as slow as it gets. It's just got to be correct, right?
Yeah.
And a whole range of options in between. And now, I mean, managers can be sometimes, say, no, I want it, tomorrow and 100% correct. And, it's like, well, you can't have both, right? So, but, so that's why we want to give people a whole range of different choices for their performance and robustness. And that's the direction that we've been taking Postgres in, is to give you the robustness by default, but the option to choose sort of how much robustness, whether it's one node robust or whether that's copied to multiple nodes before we consider it safe, or the other way, which is to increase the performance at the expense of robustness.
It's interesting. And that sounds like it's something that's being actively developed at the moment. Are there any other features that we should look forward to coming in the near future?
Well, I think there's a couple of things that are really worth mentioning along the way that people don't always understand. I think in the early days of relational databases, when you wanted to do something like add a column to a table, it would lock the whole table for like an hour while you added the column.
Yeah.
And that was one of the reasons why the NoSQL guys kind of said, oh no, like don't do that. You just want a JSON blob and you can do anything you want there and you never need to do schema upgrades. And that at that time, that was a sensible thought. Well, what we've done in the interim is we've spent a long time minimizing the lock levels that you need on your DDL commands. And as a result, there are very few cases now where we lock the whole table. You can add indexes concurrently, you can add columns in just a single metadata operation that takes no time at all. So there's a lot of flexibility now built into to Postgres, using experience running as a 24/7 operational system. So it's not the type of thing where people say, you'd better take the database down at 5 p.m. and do that now. We almost all of our systems are running 24/7, even on Christmas Day.
Right.
And what I would say is that in the rush up to Christmas, you'd probably be amazed at exactly what percentage of the world's transactions actually run through a Postgres database as part of the primary payment cycle. So when you're buying something for your loved ones this Christmas, just think about how many of those transactions are running through Postgres, and it's quite a surprising number. We're talking hundreds of billions of dollars annually flow through Postgres databases because the financial services industry trusts it.
Wow. Okay. I think on that note, that could be a good place to finish. Where can our listeners go to find out more about Postgres and the features that we've been talking about today?
Well, PostgreSQL.org is the website to visit, or if you look up Postgres, you'll find pages on the open source project and all of the commercial companies around it. But come to conferences. That's a great place to discuss your data needs. There's users giving presentations, there's people listening to things, and people chatting about what they need out of all these technologies. So it's always good to come and join in the community.
Well, Simon, thank you very much for coming on the show, and for Software Engineering Radio, this is Simon Crossley. Thank you for listening.
Thank you very much.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.